Um, Last time we started looking at quantum wires and quantum point contacts. And the idea here was we have a one-dimensional object, so this is 1D, and the length of this wire is comparable to LD. This is the diffusion length. Okay, so, and if I draw the connections, this means if this L is much greater than the diffusion length, then my electron will do such a motion. So, since the diffusion length is much smaller, let's consider L is much greater than LD case. So this means multiple electrons will do this diffusive motion because of scattering events. So this will still be a nanowire because of the dimensions that we chose, but it will not be a quantum wire. But in this case, the electron's motion is more or less something like this. Electron goes ballistically, it doesn't hit anything, and then perhaps it can do a single scattering within the wire, or it may just go without making any scatterings, and so on.
When we are talking about the electron's movement inside the nanowire, are we talking about, like, it's a carbon nanotube, for example, the electron is going right inside it, or going on the material itself?
That's a difficult question to answer. If we speak about carbon nanotubes, then where exactly electron lives is not clear because it's a quantum mechanical question. You can talk about the probability densities, but you're right. I think the probability is highest within the carbon nanotube. For these systems, I mean the systems that we are considering at the moment, actually we start with a 2D electron gas, and then by constructing channels, gates, we confine this 2D electron gas to a channels. For instance, you have this gallium arsenide layer, and then on top of that you have gallium aluminum arsenide layer, and then you have your 2D electron gas here. So when you look from the top, this whole beneath the surface, you have your 2D electron gas. And what people do typically is they pattern electrodes like this, okay? And then they apply certain bias to these electrons, and these are gates that are not in contact with the 2D electron gas. They are resting on insulating material, so they are local gates. And when you apply certain bias, then effectively you deplete electrons underneath these regions, and you end up with a 1D channel. Okay, you bring another confinement from the other direction. What else we can think of? As I mentioned in the previous lecture, for the case of metallic wires, they're always going to be diffusive unless you make them extremely short, because for the metallic wires, typically the mean free path is about like 10 nanometers, and the Fermi wavelength is about 0.1 nanometers. So whenever you have a metallic nanowire, it's typically a diffusive wire. But in the case of semiconducting wires, I think you can do similar experiments with silicon at very low temperatures, but there aren't actually many examples that you can find like really standalone nanowire. Carbon nanotubes is another example, but in the case of carbon nanotubes, it turns out that making contacts is very difficult. Making good contacts is very difficult. So because of that reason, as we'll see in a moment, this motion, I mean, we assume that we have a reservoir here that contains lots of electrons, which is our metallic contact, if you like, and here as well. And as we'll see in a moment, this assumption says, okay, I have plenty of electrons here with lots of different energies, and one electron can enter into this nanowire without any obstacles, or real obstacles, I should say. But in the case of carbon nanotubes, it has to go through a tunneling barrier. Okay, so it has to tunnel through a barrier to be able to get into carbon nanotube first. So in that case, we don't see most of the quantum wire effects that we see. So really, most of the experiments, or most of the stuff that I'm going to explain, has been performed on confined to the electron gases. Okay, and this was a very broad answer to your question, I guess. So another object that I'm going to talk about is quantum point contacts. That's very relevant to sending electrons into a quantum wire. Actually, we are going to spend most of our time discussing quantum point contacts. And the idea there is you have a very narrow constriction, okay? So the width and perhaps the length of this channel is, again, comparable to the diffusion length. So we are talking about a very narrow channel that electrons can pass through. Now, let's try to think about how an electron would move within this channel. Now, in our Drude model, even in the case where we treated materials with quantum mechanics, the idea was electrons do this scattering motion. So in the overall picture, what we look at is the average motion of the electrons. We never looked at how an electron would go through such a constriction. But now we have this constriction, and we are talking about electrons with Fermi wavelengths that are comparable to the sizes of this object. So what we will see, I'll also try to show you this in detail, but now we have to consider electrons as waves, okay, coming into this channel. And what we are going to see in this ballistic transport is that this wave will be partially scattered back from this constriction, and it will be partially transmitted to the other side. So rather than talking a small billiard ball bouncing around because of this averaging effect, we have to take into account that electron is a wave, and when I have an electron that's traveling towards this constriction, that wave will gradually evolve and change its shape, and as soon as it reaches this constriction, some of that wave will be scattered back and some of it will be transferred to the other side. And if you think about the current that is transferred from left-hand side to the right-hand side, or we'll call this source, and this is drain. The current from source to drain is no longer going to be directly proportional to, I should say, resistance times current equals to the potential difference. So what we should be looking at is rather more complicated, because now we have to do an analysis in in regards of the transmission probabilities of this constriction. Okay. So now the first question that I should answer is, why is there a resistance of quantum point contact? I sort of answered this question by saying that there is a certain probability of sending an electron from here to here, although it comes with a certain certain velocity. So the picture that we have drawn here is not 100% accurate. So we cannot say when an electron comes here, it will go through without any resistance. That's not the case, simply because there will be these interference effects and so on, as we'll see in a moment. Okay? So I should cite two references here. Now, as probably you have noticed, the papers are like 30 years old or 20 years old. So these are quite recent discoveries. And so there are two papers actually. Both have been published in the same year. Okay, one of them is by Wies et al. And the other is Raham et al. And what they showed is this. So conductance, or you can say resistance inversed of quantum point contacts are quantized in J 2e squared over h, and this is some integer. And probably you remember this guy. It's the constant that we have seen in quantum Hall effect, 1 over. I mean, we are talking about conductance now. So, but there is a difference. In quantum Hall effect, the accuracy was on the order of 10 to the minus 10, so down to 10th digit. Here, it's more like 10 to the minus 2. So we don't have as high precision as quantum Hall effect, but still you can see these conductance steps as you try to pass current through a quantum point contact. Then if you increase the length of that quantum point contact, so if you start evolving into a quantum wire, you lose these conductance quantization. It rather starts behaving like a diffusive barrier. Okay? And perhaps I should make it clear why I am studying quantum point contacts in the first place, because actually if you cover the rest of this quantum wire, this is also a quantum point contact. So that's why much of the emphasis here is going to be on quantum point contacts. Again, if you have any questions, please stop and ask. Okay. Now, let's try to find an answer to this question. Why is there a resistance in quantum point contacts? So, as I mentioned, there is backscattering of this wave. Well, the particle itself doesn't backscatter, but probabilities that what I'm talking about. So there is no backscattering at the exit or in the quantum point contact. So as we mentioned, there's no scattering event here, and there's no back scattering in this region, but the probability can scatter back from the entrance part. Okay. So let's try to figure out how a current can be transferred from source to drain for a quantum point contact. Now what we are going to use is Landauer's formula, and most often you'll see this name with another one. So typically a more general form is called Landauer-Büttiker formalism. Okay. Now what I'm going to do is this. Let's say I have a reservoir of electrons on one side, and then I have an ideal lead. Okay, so this is a hypothetical object, and then I have my quantum point contact, and then another ideal lead, and then another electron reservoir. So the idea here is to look at the current that can travel from reservoir 1 to reservoir 2. Okay? Now, when I look at it in overall, the transmission probability, and there will be some reflection probability because of the reflections at the entrance. But in any case, total probability should be 1. So this is, not at this stage perhaps, but it's a manifestation of conservation of charge. So no electron vanishes halfway in between. So transmission plus reflection probabilities equal to 1. Okay? So also I'm going to define chemical potentials for these reservoirs, mu1 and mu2. So this is the energy required to add 1 electron to this reservoir. So it's similar to Fermi energy if you think it that way. Okay? So the energies required to put 1 more electron in these systems are different. The way I adjust it is going to be in such a way that the potential is going to be, so the potential difference across these contacts is going to be mu1 minus mu2 divided by the electron's charge. Okay. So these are the energies. So I assume that I apply a certain potential difference between these reservoirs. So I have a battery connected to here, if you like, with voltage V. Okay, so that's the energy difference between these two reservoirs. Okay, now let's try to solve well, it was like, okay, you can see its ghost. Right now, what I'm going to write is this now. Current can be written as electron density times electrons charge times the velocity of the electrons. This is the classical expression that we have written. So this is electron density. Okay. And what we can write down is this, based on this equation. I'm going to say now so let's define something as Nj. Here J corresponds to 1 or 2, corresponding to density of states on side 1 or side 2. Okay. So this density of states can be written, density of electrons can be written as density of states on one side times E minus mu J. Okay. So I've written the density of electrons here and here. So what I'm going to do is this. I'll write this current as a function of energy of an electron that's going to go from this side to that side. So E times the transmission probability times density of electrons on side 1, then speed of electron on that side, V1, minus density of electron on side 2 times velocity of electron on the other side. So the idea here is, this was sort of the classical expression we had, and the assumption in this expression is that for any current, I take a collection of electrons that are moving with velocity v, but now I should reduce this down to single electron case. Still, I should be talking about density of electrons, but now I have a very important difference compared to this one, because the transmission probability when I take this collection of electrons is no longer 1. Rather, it's given by a certain transmission probability, and also the number of electrons on the left-hand side times its velocity, and this difference is actually will give me the amount of electrons that will be transferred from first side to the second side. Does that make sense? So in this case, as soon as I apply a potential difference to the contacts, what happens is that I have a collection of electrons with certain probability they will be transferred from one side to the other side, okay, with that whatever drift velocity I have. But here, the difference is some of the electrons may reflect back, and some will be transferred with a certain probability that's less than 1. So what I have to do is I have to look at the difference between this density of electrons times the velocities, and it should be multiplied with a certain probability. So this actually gives me the current that is passing through my quantum point contact. Now let's try to make more sense out of this equation. Now we can write this down as such. I have AT, then density of states on the first side times the Fermi, this is the Fermi-Dirac distribution function. Right, I'm dealing with electrons, which follows the Fermi-Dirac distribution, So I'm writing this expression in terms of this expression. Then I will have this 1 minus F E minus ED times V1. So this term here, let me write the other term and then it will make more sense. I'll explain in a minute. Then I'll have minus D2 F E minus mu2 times 1 minus F E minus E1 times V2. So this term here and this term here, sorry, this is 2. I changed my notation in my notes. I say source and drain here, so I have S's and D's there, so I changed my notation, so this is E2. And these guys gives us this. So electron can tunnel across the quantum point contact if an empty state is available on the other side. Okay, so if you think about the probability of available empty states on the other side, this is true both for reflection and transmission. If you think about it, sorry, it's the other way around. So this is transmission, this is reflection. So this gives the probability of finding that available state on the other side. So when we look at the overall expression, what we ended up with is still the same idea applies here, but now I have the transmission probability, which defines how much of that difference between the density multiplied by velocity will be transferred. Then also I write this expression in such a way that it gives me the transmission probability, or finding an available state, probability of finding an available state on the other side of the contact. In a moment it will become much more clear. At the moment it's still very abstract and unusable, but in a moment it will become much more clear after we make certain assumptions. So now the first thing that I'm going to write down is density of states on one side is equal to density of states on the other side. Okay? The reason is, there's no reason I should work with different densities on both sides. So this will be my first simplification. Okay? So what I can say is I can talk about an average density of states. Okay? And this will be 1 over 2 pi h bar square root of 2m divided by E minus, let me say Ej. Okay. And Vj, the function of energy, is going to be square root of 2 e minus ej divided by m. Okay. So from 1 over 2 mv square is equal to the energy. So I'm assuming that the energy of the electrons is the kinetic energy term. So if I plug in these expressions back into my equation, I'm going to end up with something like this. Et divided by pi h bar f e minus mu1 minus f e minus mu2. Okay. So these are certain functions that denotes distribution. If I say temperature is close to 0 Kelvin, then these two functions will look like something like this. So they'll come to certain value, and then, so this is denoted by mu1, essentially. So this is a step function. Okay, so I can write under this assumption, I can say these are Heaviside step functions. Below a certain value, it's 1. Above a certain value, it's 0, which is denoted by this guy. Same applies for that one as well. Okay, and if I can write this down as such. After this simplification comes in, the current is going to be 2e squared over, I combine these two, so I can write 2 pi, so this is h, okay, so that's why I ended up with that, and t times v, and the reason is now I have these functions, okay. So the value that I'm interested in here is mu1 minus mu2, okay. Then this is equal to E times V. So if I replace this expression back in here, that's where I end up with. So let me write this down. Let me get rid of this part. So the current is given by 2e squared divided by h times v times t. So close to 0 Kelvin, of course. Now that's an important result. It gives current in terms of some constant, which we have seen before, times a certain transmission probability. Now this means if I apply a bias, a voltage V across the terminals of my sample, the conductance or the resistance will be something that goes along with the transmission probability times this expression. So that explains why we see these conductance steps in when we measure quantum point contacts. And of course the experiments, the papers that I cited, performs these experiments at temperatures as low as 60 millikelvins. So at these temperatures you start seeing these effects, because when you start going above these temperatures, thermal smearing becomes more important than this quantization. So rather than observing these conductance steps, what you observe is more like a straight line. It starts behaving like a classical resistor. Now, what we solved is really a quantum effect. It has nothing classical in it. It is purely, it purely came out of our quantum considerations of electrons coming from certain reservoir, encountering the quantum point contact, and there's finite probability of transmission. Okay, and once we solve for this system, we end up with an expression that's purely quantum mechanical. Okay. Now, this is for general information, but this is typically called the two-probe Landauer formula. The reason is we really assumed two probes. We applied potential and measured current from the same probes. You can extend this formula to 4 probes. So I'm just going to write down the expression for general information, because 2-probe measurements are common, but 4-probe measurements are a better way of measuring things. What I mean by 4 probes, what we typically do is this. So this can be applied to any measurement. Let's say you want to measure resistance of this object. So what we typically do is we apply certain current through these terminals. Okay, so a current flows through the device. I mean, you can apply a voltage and measure current, or you can apply, if you have a current source, you can apply current, but it doesn't matter. What matters is we send a current with a known value through these 2 leads, and then with another pair of leads, it's like the ones we use in quantum Hall effect, or Hall effect simply, we measure the voltage drop. Okay, so you look at the voltage drop across within this region. Now, voltage measurements are minimally invasive measurements. You don't need to interfere with your system too much. So the resistance of this section will simply be, we know the amount of current passes through here, and I am also measuring the voltage. So the resistance of this section will be given by V over I. And this technique is, commonly used. I almost always do 4 terminal measurements in my lab. If you want to measure a superconducting device, this is pretty much the only way to go, because if you use 2 terminal measurements, the contact resistance will always be there. You cannot measure the residual resistance of a superconductor and so on. So 4 terminal measurements are more common in this business. So this is the 2-probe formula. In 4-probe formula, what you end up with is slightly more complicated, but it's still the same thing in essence. You have 2e squared h times transmission probability divided by 1 over t. So this time I wrote conductance. Okay, so it's basically I over V. It's inverse of the resistance. Same thing, essentially. I can, if you like, conductance for this one is 2e squared over h times t. And this is the 4-probe version. So rather than trying to measure, so we have voltage probes that are coming in just before the quantum point contacts. Okay. Do you guys have any questions? Okay. So let's do this quiz. This is to award you for coming early. It's very simple, really. Okay. So there are a few things that I would like to mention. One of them is the 0.7 feature. So this is more or less what you get when you do this experiment on a quantum point contact. So basically you tune this gate voltage, which defines basically the width of the quantum point contact, but it's a detail, it's a technicality that you shouldn't mind too much. Basically, by changing this gate voltage, you tune the transmission probability. Okay, so for this experiment, let me give you the paper. It's Kern and Wet 2002. Okay, so it goes from 400 millielectron volts to minus 400 to 500 millielectron volts. And this is conductance 2E squared divided by H. Then it starts from 0, and somewhere here 1, and then somewhere here we have 2. That's 1, okay. And this is what you observe. So at 80 millikelvin, makes this very steep rise. Sorry, it goes up to, of course, 1. And then here it makes another rise and goes like this. Okay, so this is at 80 millikelvins. But something weird starts appearing as you increase the temperature. So, okay, so it starts smearing out. But a feature at 0.72 E squared over H starts appearing. And as you go up to 4.2 Kelvin, this is what you get, more or less. Okay? So you lose these conductance steps as the temperature increases, as I mentioned before. But another feature here at 0.7 G or 0.72 E squared over H appears. Unfortunately, we don't know why. So I gave you this example to illustrate the point that this is like a 15-year-old paper, but still this is an active field of research, and we don't know why we have this 0.7 feature. There are certain ideas, perhaps people think that there are electron-electron interactions going on, which may result in appearance of such a step, but the bottom line is that we don't know. This one is it's conductance. It's 1 over ohms or Siemens. Okay, but it's given in terms of 2 E squared over H. So I just want to illustrate this point to show you this is an active field of research, and there are lots of things that are unknown. Yes.
So after 4.2 Kelvin,
Mm-hmm.
it just goes like a straight line?
Well, once you start heating up your sample, you lose these conductance steps. This appears, but after I think something like 10 Kelvin, you lose everything. It's just a straight line. Okay. So, which means by changing the gate voltage, now you're not tuning the transmission probability, but you're tuning more or less a classical resistance of your sample. So this gate voltage basically changed the width of this quantum point contact. That's one thing that I wanted to illustrate. Another thing how to make quantum point contacts is this. Let me see. There is it in here? Let me check. So you can demonstrate this effect, this formation of steps in metals as well. There are two experiments. One of them is you take a very sharp STM tip, scanning tunneling microscope tip. Okay. So, did we talk about STMs, scanning tunneling microscopy? No. We talked about tunneling, so I must have mentioned STM as well. So in STM, the idea is you bring scanning tunneling microscope to very close to a conductive surface, okay? And electrons will start tunneling through this gap here, and based on this tunneling, there are a bunch of different things that you can learn about the material itself. But the idea here is rather different. What they do is, on the tip of an STM, they coat with a metal, okay? They put, I don't know, something like gold, and their substrate is also gold. Then what they do is they lower down the STM tip and make a physical contact with the gold substrate. Then they start pulling it apart. What happens is, now this is the contact case, and then as you start pulling it apart, this junction here gets smaller and smaller, so it narrows down as you pull it further away, okay? Of course, I exaggerated it here, but it narrows down to a limit where you have only a few atoms remaining in the middle. And in that limit, in the beginning I said, we only see this quantum wire behavior in semiconducting objects and so on. But if you do this, since the width of this quantum point contact is now much smaller than the Fermi wavelength of a metal, you can show these conductance steps. And indeed, let me see if I can find a citation. This is by Kramer, 1997 paper. They have demonstrated with an STM tip. This is one way to do it. Another way is, indeed, it's a simpler technique. If you want, you can go upstairs and try. I don't know if you can do it, but still, it's not too difficult. What you do is you take a flexible substrate, okay, something like polyimide or PDMS, doesn't matter really, and then you create some pillars on it with some metal suspended over that feature, okay? So it's like, when I look at it from the side, okay, let me first draw the initial condition. So it's like this metal film is supported by some pillars that are higher than the rest. So it's suspended, but it's firmly adhered to these pillars. Then what you do is you have some fixtures here, and then you have a manipulator that can push from the bottom. So these are fixtures, okay, these are fixed, and then you push from the bottom. As you push, this whole thing will start flexing, and as it flexes, it will start pulling apart this gold or whatever, palladium film or platinum film. As it starts pulling, of course, you have to use a piezoelectric pusher and be very gentle with it. As you pull it apart, at some point, you'll end up with something that is very, very sharp. Of course, if you measure the conductance versus the piezo position, you can see the steps forming again. And for this one, I was very surprised to see, let me see, in this one, I forgot the temperature that they performed, but I think it was this one. There's this very interesting paper that I'm trying to find. Okay, it was the same guys. Apparently they did both of these experiments. So this is a room temperature experiment. So somehow they managed to show even at room temperature that these conductance steps are observable. Okay. So any questions? Now, when we talk about quantum, yes.
Can you explain the last figure that you told that when we lift the STM cantilever up, that barrier will become narrower?
Yes.
So, what information do you get from that?
So you're basically, of course. So we have this something called quantum point contact. Last lecture, that's what we did. And the width of this quantum point contact is critical from transition to classical regime to quantum regime. So rather than diffusive, as you make it narrower, you go to ballistic transport. And in the case of ballistic transport, this is the formula we got. The conductance, this term, is given by such an expression. It's quantized. And what you do in that experiment is that by pulling it apart, you create a narrower and narrower channel gradually. And as it becomes narrower and narrower, at some point you start electrons doing this ballistic transport, and the conductance is quantized. Okay? That's the information, guys. So same thing down there. As you pull apart the two metal films, the constriction between them becomes narrower and narrower. You observe quantization again. Any other questions? Now, there are two more things regarding quantum point contacts, and this is really the most bizarre, to me at least, aspects of these quantum point contacts. Now, by themselves, okay, they are interesting, we quantized, so what? But when you start bringing these resistors, like quantum point contact resistors together, interesting stuff starts emerging. Let's imagine I have quantum point contacts that are in series. Okay, so it's like I have this resistor, another resistor connected in series. And let's assume I have the exact same arrangement and so on. So the assumption would be conductance of the series arrangement, or let me write down the resistance, since it's for the Ohm's law. It's going to be something like, let's say this is 1, this is 2. Resistance of the first plus resistance of the second. So this is the classical way of doing it. But as it turns out, this is not the case for quantum point contacts. This is no longer valid. The complication arises from here. Now, first you have your electron coming in, okay? And then there is some reflection probability. So there's some transmission probability and some reflection probability. That's okay. Then once you're in here, once you pass through here, same thing happens here. There's some reflection probability and some transmission probability. But now our first, one of the assumptions break down. We assume that no waves comes from here to the back. But now we cannot say that because I have a reflection of this electron wave coming back. And then there will be multiple reflections within this region. So now I cannot treat this system as sum of two individual quantum point contacts. Rather, I have to treat this whole system as one. Now, the algebra of solving such system is indeed quite complicated. So let me see how much information I put into my notes. Well, not much for that reason, probably. So, at least I should have included, let me see. Yes. So, perhaps I can write down the, let me see. At least I can try to plot you this graph from this experiment. There's this paper from 1988. It's one of the first papers that I cited for quantum wires and quantum point contacts. And they tried this thing at 300 millikelvin. And what they found out is, depending on how you change the width of these quantum point contacts, you can sweep the resistance. So, of course, it's going to be a three-dimensional graph. On one side, you have the gate voltage that controls the first point contact, and on the other scale, you have the gate voltage that controls the other contact. If you're interested, you can check the paper. But the interesting thing is, under certain condition, so it comes something like this. This is resistance. Under certain condition, resistance goes down to 0. So you add two resistors in series, and you end up with zero resistance, or you may end up with zero resistance. So it's very difficult to draw, but it's a complicated 3D surface. But at some point, under certain condition, this thing goes down to 0. So again, that's rather difficult to solve for, because now I have to take reflections from here into account. So it's a series of equations that you have to solve. But if you solve this set of equations, it's rather straightforward to show that under right transmission probabilities, so which translates into having right T1 and T2s, you can bring resistance down to 0. So electrons start just passing through these series of point contacts. And that's a very interesting outcome. And that's a purely quantum mechanical effect. Another way to connect these quantum point contacts is in parallel. So what you can do is you can have two quantum point contacts. Okay. So, I don't know, you have something like this. They are connected to a larger reservoir. Okay. Now, in this case, I have this electron reservoir, and my electron has equal probability of going through quantum point contact 1 and quantum point contact 2. And we have seen something similar to this. We have done such an thought experiment, indeed. Now, again, when they come out, now you are describing your system with electrons, and when they come out, there will be interference of these probability waves. Okay, so you may end up with, if you like, oscillations depending on how you set up these quantum point contacts when you try to measure the resistance. So the resistance can oscillate depending on how you set up your quantum point contacts. But there's one more interesting experiment that you can do in this configuration. Let me try to see. So if you apply magnetic field to this system, and the way you apply magnetic field, for instance, you apply uniform magnetic field, but you change the size of the constriction, so you don't have the exact same openings here. And what you get is Aharonov-Bohm oscillations. So if you remember, in the case of Aharonov-Bohm effect, we had a ring, okay, of something like this, and in the center we had a uniform magnetic field. And this magnetic field had an effect on the phases of the electrons that goes through left or that goes through right. So a phase factor will be gained by one of these electrons. So actually both of them gains. One of them advances by some phi over 2, the other one retards by minus phi over 2. So the overall phase gained by the system is like phi, but still there will be a phase change. If you do the same thing to these parallelly connected quantum resistors, you can observe an effect similar to Aharonov-Bohm effect. Based on the dimensions, you may end up with different responses from these resistors. And it looks something like this. This is a Moon 1997 paper. And this is 0 Tesla, this is 0.1 Tesla, this is 0.2 Tesla. Likewise, it goes to negative magnetic fields. And at 0, there is a certain resistance, but then you start seeing these sharp peaks, a resistance that basically comes from the interference of the electrons. So again, it doesn't behave as two resistors connected in parallel, two classical resistors connected in parallel, but rather it contains quantum, I can say, quantum behavior. So is there anything else? Should be talking about quantum point contacts. The reason why I spent so much time on this is simply because any quantum wire will have a quantum point contact at its end. Because you start with a large reservoir and then you confine it and you end up with a constriction. So you try to squeeze your electrons from a 2D or 3-dimensional reservoir to a 1-dimensional object, and at the tip of the quantum wire you will have quantum point contacts. So that's why I spent too much time on it. When we talk about quantum wires, there's one last thing that I should perhaps mention, because it deserves mentioning, is carbon nanotubes. If you look at the old books, the way they talk about carbon nanotubes is it's rolled up sheet of a single layer graphite. Okay, they didn't know about graphene. The name, at least, wasn't that widely known. So it's a rolled sheet of graphene. And the way you roll it onto itself matters, because there are various ways of rolling it up. So if you take a piece of 2D object, then you will immediately realize that you can meet its ends like this, or you can distort it in various ways. Of course, it doesn't have to be rectangular. You can have an oddly shaped object, but even this forms a tube. Imagine that this extends. So there are various ways of stitching the ends together to form the tubes. And the way you stitch these ends determines whether the carbon nanotube is metallic or semiconducting. So the edge stitching determines the metallic or the semiconducting nature of the nanotubes. Now, let me try to see if I can draw I'm not sure if I can really draw this thing. Let's see. So and then let me go this way. So let me do. Okay, so this one, if the edge is like this, the end of the carbon nanotube is like a zigzag. Of course, I have to show it on a carbon nanotube, but it's even more difficult to draw that. But believe me, there are two ways to wrap a carbon nanotube onto itself. One of them is called the zigzag. It just goes like this. And the other one is the armchair. So the armchair is this configuration. Okay. The reason why it's called armchair is that it supposedly looks like an armchair, but to be honest, I never get my head around it. Really,
You were able to draw something, but we are not able to draw it.
What's that?
You were able to draw something, but
Oh.
we are not able to do anything.
Okay, well, still.
It's difficult, yeah.
But no, I mean, how does it look like an armchair? I'm not talking about drawing. I don't know. Somehow it's named armchair. Okay. Okay, so
I have a question for you. What parameter determines that the carbon nanotube is multi-volt nanotube or single?
well, if you have multi-walls, so if you have carbon nanotubes that are wrapped around each other So rather than taking a single sheet of graphene,
Yes, I know that.
yeah.
But during synthesis,
I have no idea. I have no idea, absolutely. When I was doing my PhD, my group was also working on carbon nanotubes, and we had a furnace dedicated for carbon nanotube synthesis, but it was like what is it called? Like black magic, you know? You just send gases in, then you have this precursor. It was some iron oxide compound, and they would send hydrogen and methane into the furnace at about 900 degrees Celsius. Then they ended up with carbon nanotubes, and they didn't know really how. I think they know the mechanics, but they always got single-walled carbon nanotubes, and from time to time they could get metallic or semiconducting ones. My group was interested in semiconducting nanotubes, not because of its electronics, but because of the its surface properties. They were looking at the absorption of certain atoms on carbon nanotubes, especially the way it's rolled was it would allow these adsorbates to go from one phase to another phase. So they were looking at phase transitions of these adsorbed atoms on the surface of nanotubes. And it was just like they had an array of devices. The device geometry was something like this. So they had platinum contact here, another platinum contact here, and then another platinum contact at the base to be used as a gate. And they would put this catalyzer, this iron oxide something, here. Then what happens is carbon nanotubes grows out of this thing, and then once it reaches to certain height or certain length, it somehow the attraction, the forces here are stronger than the energy required to keep it straight. So it falls down onto the other contact. So they would end up with, most of the time, single nanotube crossing through a junction. And they literally had like hundreds of devices on a single chip. And they would measure every single contact to see if there is a carbon nanotube crossing. If they have a metallic carbon nanotube, they adjusted the amount of bias in such a way that they would burn the metallic nanotube because of the too high current passing. But if it is a semiconducting, then it wouldn't burn that one. So with that, they could get rid of metallic carbon nanotubes. If also there are multiple crossings, like one metallic, one semiconducting, and so on. Anyways, but I've never seen or heard that they are complaining about, okay, this is a multi-walled carbon nanotube. Somehow they would always get a single-walled carbon nanotube in that case. So I really don't know how you...
The synthesis of the single-walled carbon nanotube is some kind of physical, but chemical.
Probably. So yeah, probably this catalyzer, the idea was that it dissolves this, it dissociates carbon from hydrogen in the methane somehow, and then it results in the structure. But to be honest, I really don't know the mechanics. So we have metallic and semiconducting tubes, but pretty much none of the experiments that I mentioned have been performed on carbon nanotubes for one very simple reason, because carbon nanotubes are very difficult to make contacts with. Whenever you make a contact with a carbon nanotube, it's not an ohmic contact. It's not a proper contact. What you get is you have the carbon nanotube, and then you have a tunnel barrier, and then your metal. So whenever you put contacts on a carbon nanotube, there's always a tunnel barrier that somehow you cannot get rid of. So what happens is that any electron that you try to send from metal to the carbon nanotube has to go through this tunneling barrier, which basically ruins that quantum point contact nature. So as soon as electrons tunnel, now they're in the quantum wire, but the transport through the carbon nanotube, and as for the measurements, it behaves as a classical conductor. So you don't observe any of the conductance steps that we measure. There's, I think, one experiment, at least mentioned in this paper. I'm not an expert in the field, but there's one experiment that people performed. So what they did is they, again, took an STM, and then they attached a carbon nanotube. Okay, well, I don't know why I drew it that way, to the tip of the carbon nanotube. And at the base, they had mercury, okay, liquid mercury. And again, they connected bias to this one and tried to measure the conductance. And this way, they could show these conductance steps. Somehow, this liquid mercury, once it's dipped in it, allows a slightly better contact than usual. So they could show some very smeared conductance quantization. But anyways, it's not easy to perform the experiments that I mentioned on carbon nanotubes. So it's 1991. Yes.
Like you mentioned that we have different dimensions to roll the
Mm-hmm.
different sheets. Like we mentioned, this is called edge stitching.
Mm-hmm.
So it determines that whether the nature of the material is metallic or
Yes.
stable. But when we discuss the graphene, it is only a single
Mm-hmm.
layer of carbon atoms with almost no band gap.
Mm-hmm.
So how it behaves, like shows semiconductor properties.
So are you talking about like what happens to the electronic bands when I roll it over onto itself? Well, to be honest, it's, at least for my side, it's a difficult question to answer, because I mean, probably if you go to Oğuz Hoca, he can give you a much better answers, but to be honest, I don't know exactly what mechanisms are involved in changing or opening of this band gap. But I mean, it's not, to me, to be honest, I never thought about it, but it's not any different than having, okay, in a single layer limit, you have this Dirac cone for graphene, and then when you go to bilayer, then you have a small band gap that opens up, right? So, I don't know, some sort of interactions results in change of the energy relation, the dispersion relation. But to be honest, I don't have a definitive answer. Let me see. I mean, here I've seen the band structures of metallic and semiconducting wires. In the case of metallic nanotube, it's just the bands overlap. In the case of semiconducting, there is obviously a gap, but really, I don't have a fundamental understanding of how or why in one folding direction you end up with a metal, and in the other one you end up with a semiconductor. I don't know.
Maybe
Yeah. Right, so in the remaining 10 minutes, I don't want to start single electron tunneling and single electron tunneling transistors, but let me try to give you a brief overview of what we have done and what we are looking at in a broader perspective. So the way I look at things, starting from 1960s and onwards. So, of course, the theoretical studies, it goes back to 1940s actually, because as soon as people start understanding quantum mechanics, they try to solve real problems with this new tool. And as early as 1940s and 1930s, people started applying quantum mechanics to solving complicated problems of solid-state physics. But starting from 1960s, people started realizing that there's a whole new physics that exists in materials simply because of quantum mechanics and interactions. And till 1980s, there are lots of different theoretical models and lots of different players that we see. So this region is like more of theory of what we studied so far. And starting from 1980s, the important thing is that we started doing molecular beam epitaxy and MOCVD in a very controlled way, so we could synthesize materials in much purer and in a much controlled way. So people started making these syntheses on gallium arsenide layers, and they could dope it with aluminum and indium and so on to modify the properties. So using these, they could make 2D electron gases that they can study. And starting from 1980s, we start seeing lots of interesting stuff like quantum Hall effect. And then these quantum wires and quantum point contacts, quantum wires, these are more like the child of 1990s, but still the people started realizing that with the understanding of quantum Hall effect, they can investigate these bizarre quantum effects in two-dimensional systems. And then 1990s were more like, I would say, discovery of new materials and applying the ideas that we had there. So carbon nanotubes was among them. And people spent a lot of time studying, again, 2D electron gases during this period. And then around 2000, we can say 2003, then graphene comes into play. So I'm not sure if you can see it at this moment, but graphene sort of makes these guys useless, because you can show quantum Hall effect in graphene. So it's a 2D electron gas. It's a 2D electron gas that you can tune its energy with a backgate or with a gate. So sometime, I think around 2005, so this is late 2003, but even at 2003, before the publication, people started hearing about the stories. They show quantum Hall effect and also Berry's phase in graphene. So then the landscape started changing, because now you have a completely new system that's more accessible, that's more controllable, that's easier to get hands on, because all you need is Scotch tape and a highly ordered graphite film, so you can exfoliate as many times as you can. So this was more available. And then starting from that time on, people started looking at the old papers and old theories and started applying them to these new materials. So basically, many things that we see on the graphene, if you dig deep enough, you can find several papers on 2D electron gases that has been already done. So it's a re-demonstration of the concept. So the actual stuff took place in here. But then people started realizing that graphene is not as simple as a simple 2D electron gas. Rather, electron-electron interactions are important. Also, people started realizing that graphene is not the only member of this family. There are many other members named transition metal dichalcogenides. So it's in the form of a transition metal and selenium, sulfur, tellurium that makes a compound with it. And you can obtain monolayers of these guys. They are semiconducting. And for many cases, like if you take molybdenum, tungsten, vanadium, niobium, and so on, these transition metals, they show electron-electron interactions as well. So now we have systems that we have 2D electron gases. We can show these effects, but in a controlled way, we can also show how electrons interact with each other, how electrons interact with the lattice, the crystal itself, and so on. So that's sort of how I see the current developments in the field, and I just wanted to share this with you. So next lecture we are going to start looking at single electron tunneling transistors, and we'll try to develop an understanding of how the conduction in a single electron tunneling system will take place. And once we are done with single electron tunneling, I'll start looking at superconducting devices. So I'll talk about superconductivity. Then after that, I'll start talking about these 2D materials, 2D systems, and very recent experiments that has been done on mesoscopic 2D materials. Okay. Any questions? All right, so I think we'll do the exam on 14th of December. Again, probably at 5:40. Okay. I'll let you know. I'll make the announcement. All right.
Second lecture, the way you conduct in first lecture.
What's that?
Quiz.
Okay. You missed it. So what?
You always conduct your second lecture.
Never trust the professor.
Well, I waited till